Mr. Wade, can you hear me? So is your Arduino not connecting to your computer? And Josh, does your Arduino connect to your computer? Okay. Mr. Wade, does your computer not connect to your, or does the Arduino connect to your computer, Mr. Wade? All right. Josh, I'm going to have to work with you after class to get it set up. Oh, okay. All right. So let's go ahead and pull out your Arduinos and we kind of go over a few of the basics again. And I believe last class we got light to shine, but stayed on constantly. So this class I'm going to go, we're going to do a little bit more detailed stuff, kind of one of the basic introductory codes. But on top of that, I'm going to throw in some calculus, some math, and try to really explain and hammer in the fundamental concept of electricity, which is Ohm's law. Cool. So, first, a few quick things. Let's go back over. Where's the picture? Okay. I've had similar storms too, or I think they're coming down this way. All right. So, excuse me. A few of the main things here. One, this is of course how it connects to your computer. Two, this rail here that says power. This is going to be how we're going to reference different power voltages, but we're not going to be doing it tonight. Excuse me. But this is where power both comes out and comes in. Of course, V in is power in. All the GNDs are the grounds, which are exactly the same. Every GND is exactly the same. They all share a common ground. And we are going to be using digital pins over here tonight. All right? We're going to be using probably 13. We might get to a few more. I don't know yet. We'll see how fast this goes by. An LED is, what is a LED? Or what does a LED do? That would be more the question I'm looking for. Doesn't smash atoms, Tyson. It's not fusion. But close. An LED, yes, it smashes electrons into protons to emit electromagnetic radiation. One second, Josh is having audio problems. Can you hear me, Josh? All right, but the main point of the LED, or the diode part, is that it allows electricity only to flow in one direction. All right, that's the main thing. And we went over and we hooked up the most simplest circuit you could, which was just a light hooked up to a resistor, hooked up to a power supply. This power supply representing battery. A circuit is actually a Latin root word for circle, so everything has to be kind of connected in together. Right? You can't have any open connections, or the circuit will not work. All right. let's just kind of jump right in. And for this circuit 2, I'm going to go ahead and I am going to break it down Big Bird Cookie Monster style for everybody. So everybody understand kind of what I'm doing here. So this is the circuit I'm going to hook up. All right, it's not going to be exactly like this, but it's going to be similar. Actually, that's not the circuit I'm going to hook up. I lied. Where's the circuit I'm going to hook up? That's the circuit we're going to hook up. All right. So again, your Arduino should not be plugged in. I don't want your Arduino plugged in right now. I do want you to pull out a 330 ohm resistor, which is orange, brown, gold, a red wire, a green wire, and an LED. I do not care what color LED. So pull out a red wire, a green wire, a orange, brown, gold resistor, and a LED. I do not care what color. Raise your hands when you have all that out in front of you. Can you hear me, Josh? Okay, if you have it still in, I want you to unplug it. If you still have the circuit hooked in from last class, I want you to unplug it. And that can be your components that we're going to use. Okay. Again, raise your hands when you have the all set components. Yes, you can use those wires. We're just going to hook them up slightly differently. This is for real, or the Spark Fun kit. I want you to get all the stuff out of the kit that we sent you. Red and green wires, any color LED, and a 330 ohm resistor, which is orange, black, gold. I'm gonna walk you through the LED stuff, Mr. Wade. Raise your hands when you have all that stuff out. Cool. Awesome. All right. Mr. Josh, I know you're probably still catching up, but I'm going to kind of move on. I will repeat the steps here a few times. All right. So, how I want you to hook this up, and we're going to start with the power. So I want the red wire to be plugged into pin 13 of your Arduino. Make sure it's plugged into pin 13 and not the G&D, pin 13. I want the other end of the wire to be plugged into A4. So one end of the red wire in pin 13, the other end in A4. I want the long end of the resistor plugged into C4 and the short end plugged into C5. Again, that was the long end of the resistor is in C4. The short end should be in C5. Take the resistor. All right, and so now we're right here. So we got this part done, So now we're going to hook in the resistor. I'm going to hook it into E5, and the other end is going to be in E13. I'm going to take the green wire. Hang on one second, Josh. I take the green wire. I'm going to stick it in A13, and the other end is into any G&D on the Arduino. Any G&D. So here, let me walk back through that one more time. I'm going to put hands down. I'm going to repeat the steps, Josh. Yep. All right. I'm going to repeat everything one more or a few more times here until I make sure everybody has it. I want one end of the red LED plugged into pin 13 on the Arduino. Pin 13 on the Arduino. I want the other end of the red wire to be plugged into A4. A4. I want the long end of the LED to be plugged into C4 while the short end is plugged into C5. So the long end of the LED should be plugged into C4 while the short end is plugged into C5. I want one leg of the resistors to be plugged into E5, E5, and the other end of the resistor to be plugged into E13, E13. I want one end of the green wire to be plugged into A13, A13, and the other end into GND. Raise your hands when you think you have that. Okay, Josh, you need to pull out a red wire and a green wire, a LED, and a resistor. The 330 ohms resistor, the same one we used last class, which should be orange, orange, brown, gold. Do you have all that? All right, let me go through that again. Yeah, I kind of went kind of fast that second time. All right. So, if you're completely lost, go ahead and unplug everything. If you have it set up, fine, leave it as is. But if you're lost, go ahead and unplug it. I want one end of the red wire plugged into pin 13 on the Arduino. So that's right there, right here. All right. I want the other end of the wire plugged into A4. A4. So one end of the red wire is in pin 13. The other end is in A4. The long leg of the LED is plugged into C4. And the short end is plugged into C5. The long end of the LED is plugged into C4. The short end is plugged into C5. I want one leg of the resistor. It does not matter which leg. I want one leg of the resistor plugged into E5, E5, Echo 5. And the other end of the resistor to be plugged into Echo 13, E13. I want one leg of the green wire, to be plugged into A13, and the other end is in GND, in any GND. It doesn't matter which GND, just a GND. All right, raise your hands when you think you got it. Mr. Roseman, you got it, sir? Awesome. All right, let's move on. So here, go ahead and plug in your Arduino. All right, make sure you have whichever COM selected that you need. And go, oh, my Arduino's not plugged in. Should have if I follow my own instructions. There we go. All right. Yep. And then go to File, Examples, Basic, and Blink right here. And you should see something like this. And go ahead and upload it. right, and then let me know what happens. Raise your hands when you have a blinking light. Make sure you have the right comm selected, Mr. Wade. All right, can you stick around after class so I can help you out with that? Yeah, let's after class. I'll stay over to try to help you out. So to get to Blink, you go to File, Examples, Basic, and Blink. Can you hear me now, Josh? Put your hand up. For everybody that's blinking, let me know. It shouldn't blink randomly. It should be blinking. All right, Josh is going to log out. Who said, whoops. Somebody said mine's not showing. Mine. Yes, you can close the other Arduino program. Who said mine's not showing? I missed it. I think it was Jacob. What do you mean yours not showing?
Mine doesn't show anything, and it's what is supposed to blink? The green?
The LED that we plugged in.
Oh no, it's not blinking at all, and I have it plugged in.
All right, did you upload the code?
Which code?
All right, so go to File, Examples, Basic, and Blink.
Yeah, I did that, and it didn't show. It pulled up. It didn't pull up anything.
Like, you don't see anything here like this?
Nope. I did that right there, and it didn't show anything.
That's weird. Here, I'll just send you this one.
Okay.
In the chat window, just copy and paste. All right, somebody else said something. Mine blinked for a while, then it stopped. Dennis. What's going on with yours, Dennis?
Yeah, it just started up again.
You might have like a loose connection. One of the wires might not be plugged in all the way, or one of your LED might not be in all the way. Okay, so when you upload it, first up the light should blink kind of randomly, and then it starts blinking at a steady pace. All right, I only have 3 hands up. Josh, are you tracking along? Okay. Yep, click upload right here, Mr. Jacob, or Mr. Murray. No worries. All right. Cool. So now let's kind of explain. I'm going to kind of explain a few things before I move on really to what the coding is. You need to understand certain other elements here. So I mentioned it before about Ohm's law. Ohm's law is a relationship between voltage and amperage. But what is voltage, what is amperage, and what is resistance? Did I give my little spiel about resistance and electrons moving through it last class? Or how resistors generate heat? Yay, nay, I did, I didn't. Okay. All right. So Ohm's law was done by a guy named George Ohm back in 1827, a long, long time ago. And it said that the electromotive force acting between the extremities of any circuits is the product of the strength of the current and the resistance of that part of the circuit, which is a very complicated way of just saying V equals IR. The sad part, Dr. Ohms was actually fired from the school because they saw that they thought his theory had no actual applications. Turns out, yep, they were wrong. Well, there's voltage and there's amperage and then there's resistance, and I kind of explain what resistance is, but the two main ones are the voltage and the amperage. First up, which one of these is the killer? Have I told you that one? Which one of these can kill you quickly? Amperage, exactly. All right, hopefully you'll understand why here in a minute. So let's look at what voltage is. Voltage is potential electric energy. That's a kind of a weird way of saying voltage equals the charge over 4 pi epsilon naught times the radius, which is a really complicated way of just saying V equals dW over dQ, which is just a slightly easier way of saying the change of energy over the change in coulombs. Or to say it simply, if you touch anything that has a high amount of voltage, your arm will tingle. Q is the charge of electrons, which is 1.602 times 10 to the negative 19th, which I think is kind of amazing that we can know that the charge of any electron in the subatomic space is 1.902 times 10 to the negative 19th. So, and voltage is kind of like the pressure behind the electricity. And let me get over the amperage part, and I'll explain. Hopefully everything will tie in together. I is current, or your amperage, and I use current and amperage interchangeably. They're both accurate. Is the motion of a charge from one region to another. Now, another way to think about what amperage is the relationship in velocity. Now, velocity is a measure of speed, like miles per hour. If you go from 0 to 45 in 1 hour, you went 45 miles per hour, etc. So there's the actual equations for amperage. It's dq over dt, which is similar to velocity, which is just ds over dt. Or equals epsilon naught times the change in electric flux over dt, which is just a complicated way of saying I equals q over t. One way of looking at it is a simple way is if you have 6 electrons, just say random 6 electrons flowing in some direction in 2 seconds, you could say that you have 3 amps. Now that is not a very accurate example, it just kind of throw some numbers in there to kind of get it in your head about the change in dq over dt. Now here's where kind of this is an analogy that's always used for the difference between water or volts and amperage. Volt is the pressure, say, coming out of this hose right here. All right, it's however much water is coming out of the pressure behind this. Amperage is the number of water molecules coming out of this hose per second. So however many number of water molecules that are dumping out on this floor per second is the amperage of this hose, which in this case is probably a whole heck of a lot. Now if you hold back the water, but still have some of the same pressure coming out of a smaller hole, you thereby increase the amperage. So you're making the water come out faster, or the water molecules come out faster, they're increasing the amperage. This is just to give you a visual representation of it. It's the one that's always used. However, the more you dive into what electricity is, the more this analogy does not hold up. So I just want to say that it is not always the case. Now, in the case of the circuit that we're doing right now, try to give you a more hands-on or more numerical approach to it. that light is turning on and off every second. So I bet that you can calculate the exact number of electrons flowing through that LED every second. Y'all think we can do that? Which if we could, that's going to be pretty daggone cool. We can calculate the exact number of electrons that are flowing through this light bulb. So essentially we know the exact number of electrons that we're smashing into protons to create the electromagnetic radiation, to create light that's making it go blink, 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 that you all can't help but look at every now and then. All right? So, and there actually is a way of doing that. So in our first code that we're looking at we turn an LED on for 1 second. How many electrons pass through the LED? Well, if you made your light go fast, you can figure out the same thing too. It's just a simple little algebra. So if I equals dq over dt, now we already know we know two of these variables. We know the amperage. I measured it. I literally took my multimeter out and measured it earlier. And I know it's going to be 0.009 or 9 milliamps. I know the time that it's going to be on. It's going to be on for 1 second. So if you increase the seconds, you just increase the factor here. So if this is the formula for I need to know the charge of Q. So I just simply moved dt over to I. Now the reason I got rid of the dq and dt's is because I already know two different values, so I don't need to know the difference in, I don't need to know the difference in charge for dq. I can just say that as q. This is calculus, or this is derivatives here. The derivative of the charge and the derivative of the time. So with a few little simple algebraic manipulation, I just pull dt, multiply both sides by dt, leaving me with I amperage times time equals Q. So, and it's on for 1 second, so I already know the amperage is 0.009. So 0.009 for 1 second, saying that I have 0.009 coulombs, which is what Q is measured in, 0.009 coulombs. Now, using another relation of Q over E, which is charge in coulombs over coulombs over the charge of an electron, we get the number of electrons. Now, this is similar to the molar ratio. So if I take 0.009, divide it by 1.602 times 10 to the negative 14th, I know now that at every second I'm passing a whole bunch of electrons. Yeah, so since there is a linear commonality between all of these, if you divide that number or multiply it by however much time you're using, means that's going to be how many electrons are actually flowing through your circuit. This is a college level physics 2 stuff, all that dq, dt stuff, otherwise known as the class you realize that you are not as smart as you thought you were class. So don't be nervous. Did that sort of kind of make sense? Did anything click in your heads there? Did that just go over your heads? Yeah, I know that's kind of rough there. I mean, this is not easy stuff there. I kind of think y'all can handle it, but the important thing to realize is two things. One, voltage is a measure of energy over coulombs, which is a charge. So it's a measure of energy over coulombs, while amperage is a measure of charge over time. Amperage is the only one in which is dependent on time. Voltage is not. Cool. All right, so now let's move into what the code is doing. Where's the code? All right, I'm not going to cover all this stuff. know what? I think I do it better explaining in the slide, so I'm going to go ahead and use this. Now, your code might be slightly different from mine, but it's going to be very similar. Instead of this here, you might just have 13 right there, and 13 right there, and 13 right there. It's the exact same code. So let's look at what this is doing. First up, this is just a declaration of a PIN number. This is like saying, like we did in Scratch, where we said int score or score equals whatever or speed equals whatever. This is very similar going on right here, except for this time I'm designating it as a PIN number. All right, and we won't get into anything in which that might compromise itself, so I'm not worried about that. There is tricks that sometimes you can't do this, but we're not going to worry about it. The void setup part. Void setup is exactly what it sounds like. It sets up the code. It labels whatever pins I want as outputs or inputs. I can initialize variables. I can start up libraries, which we'll cover later. I can do all kinds of things. The important thing about void setup is that it only runs one time. So once the Arduino kicks on, void setup only runs one time. Yeah, if yours does not have the int LED, you just might have 13 right there. It's the exact same thing. It's just, you know, instead of having this here, they put 13 there. All right, I can say, I can change this LED here. I can change this word. This is just a word that's made up. I can change that to I can change that to int Wade if I wanted to. Sorry, Wade, you're just first name I looked at. All right, I can change that to Wade and then put Wade there, put Wade there, put Wade there, and it would be the exact same code. All right, does not matter about LED. The Arduino does not care that it's an LED in any shape, way, or form. Doesn't care that it's an LED. It's still going to do whatever it's told. Now the void loop part gets to be a little bit trickier, but not much. So the void loop part, how this runs, this is, well, one is a loop because I know that because it says the word loop in there, but how is it a loop? Well, the void loop means it's going to run forever and ever and ever as long as it has power. It means it's going to run down to here, and then it's going to come back up to the top. It's going to run down to here, and it's going to run back up to the top. It's going to run down to here, then it's going to jump right back up to the top, so forth and so on until it does not have any more energy to run the loop anymore. If you invented a perpetual motion machine, it would run that code forever and ever and ever till the end of time. Indefinite loop, exactly, Mr. Wade. The digital writes, LED, which is just 13, which is high, this is saying that I'm turning that pin on. I'm turning that pin 13, on. All right? That's all that's saying. The delay 1000, the delay 1000 is just 1000 milliseconds, or in this case, 1 second. So I'm delaying it for 1 second, thereby letting it turn on and off for 1 second. Feel free to play with these numbers if you want to make it go faster or slower. You always have to re-upload your code if you make changes. The digital write LED low, that's just saying that I'm, well, now it's off. So this is high, that's off. The digital write, all this digital write stuff, this is just signifying that I'm using the digital pins. How these words, see, some of these words have certain colors to them. These are orange. This one's blue. This one's blue. Stuff like that. These are what's known as keywords. So certain keywords have specific functionality in Arduino and most any other languages. In any other languages, and you cannot use those words for anything other than what they are specified for. If you do, the universe implodes and we all get sucked into oblivion, then the doctor has to come and help us, and he time travels back and forth, he smacks you on the head for using the keyword for something else, and then the world is safe after that. So unless you really want to be the doctor because you blew up the world, don't use a keyword for any other thing other than what they're intended for. And the new doctor is really mean, so I don't think any of y'all want to be him. So the high and low part, this is one thing I do want to touch on real quickly. How much time I got? I think I got plenty of time. the high and low. So everybody's heard of binary, right? Just 0, 1, 0, 1, 1, 0, whatever. 1, 1, 0. All right, pretty simple stuff. So one thing that I like to point out here that what these numbers are is, first off, a computer does not understand 0 and 1. It does not understand what the concept of that. What it does understand is electricity on and electricity off. That's all it really means. So this high, right, is saying that it's equal to 1. Low is saying it equal to 0. So when you think binary and you say 0, 1, 1, 0, whatever, right? So the 0 just essentially means there's no electricity. 1 means there's some electricity going through some circuit of the computer. This is where the 64-bit, 32-bit, all that other stuff comes into play. And on-off, exactly. It's just electricity. That's why a lot of computer math is based off the power of 2, whatever that is. I'm too tired to think. All right. Does everybody copy, capiche, understand? Do I need to explain anything again? Am I speaking German? I know I'm not speaking Spanish. All right, cool. So let's move on here. Wow, we kind of went through that stuff. Y'all are awesome. All right. Pin mode is a certain keyword that sets the pin modes to either an output or input. Output as in essentially just outputting data or electricity. Input means it's taking in electricity or data or bits of information or all kinds of other little things. One thing I wanted to comment on. I forgot. I'm sorry. I'm about to go back up, but give me 1 second. Yeah, we did all that. Okay, we'll move on. But one more thing. So back up here when I used the water analogy. Now, this, like I said, it just gives you a visual representation of what voltage and current is, but it doesn't hold true for all cases, especially when So let me ask y'all this. So not in the case of this, but let's say this is an actual circuit and this is the voltage and this is the ampere, right? And let's say I put my thumb over the water hose here, or I put a resistance in the circuit. Let's just say I put a resistor in this circuit. Would I be increasing or decreasing the amperage? Let's just say this is the voltage supply, and here I put in a resistor. The intuitive thing, can we overclock the, yes, Tyson, you can, but don't do it. You're actually, it's kind of, intuitively, you kind of think that you're increasing the amperage because, well, this young girl is getting shot in the face with a whole bunch of water pressure. All right, that's how your mind generally works. But if you look at the mathematical relationship, and here I'm going to use Ohm's law of triangle. B, well, it's a horrible triangle. B over IR, and this is the same thing, saying B equals IR. So I equals V over R, right? So as I increase the resistance, your voltage or your amperage will actually decrease. All right. So but it's also kind of like a double-edged sword to that too. So if D was 12 and this is 1,000, all right, that's going to be 0.012. However, which is 12 milliamps. However, if I add another zero to it, it becomes 0.0012. Now, now, like I said, it's kind of like a double-edged sword to this too, because I don't know, should I explain this or should I not? Because the resistance in this case, in which we're just using resistors, is generally holds true. But also, you would think that there would be a limit to how many resistors I can pull before I can pull out pretty much any amperage. Well, that's not necessarily true, because you think if I put if I did this 12, and then, I don't know, 1 million ohms for some reason of resistance, I would get some ridiculously small number. It's not always the case. There's different ways of hooking up resistors and etc. So essentially, the circuit, whatever circuit you're going to make, the more stuff you add to it, right? And this is kind of counterintuitive to what I just said. Just know that I don't need the truth. Promise. All right? Depends on, the amperage depends on how much stuff is pulling the current out. For example, when we get to it, we slap a motor in here, right? And a motor will actually pull out a whole lot more amperage, no matter what the resistance. All right, so we will get to that. I'm going to try to put more Ohm's Law stuff in here because it does get kind of mind-boggling, and I'll try to break it down. All right, did all the other stuff make sense as far as voltage and amperage? Think you got somewhat kind of an idea on it? All right. And I think that's pretty cool. I don't know about y'all, that I can calculate the exact number of electrons going through a circuit. That's pretty sweet right there. And that was just simple algebra stuff. I didn't use any calculus other than I knew that dq over dt was the derivative. All right, let's move on. How much time we got? 15 seconds, 15 minutes. Yeah, multiple LEDs. Okay. So this is the first time I got into this circuit, so I'm going to bear with me just slightly. I haven't had a chance to look over these slides. I didn't think I would get this far. Oh, not 8. Is it here? Oh, it's not there. This one? Yeah, okay. This is it. Alright. Alright, I'm not gonna... These green objects are called LEDs. There you go. Good job. I'm not gonna waste too much time on this stuff. These are resistors, right? And these red bands on there, or the bands on there, denote different values. This one, red is 1. I know that much. So it's like 111 maybe, or 110. I don't know. I can never remember. I have an app on my phone that tells me, so I don't ever remember the color codes. What do resistors do? They resist electricity. Resistors are used to limit voltage and current. I don't like the phrasing there because that's not true. It is used to limit voltage, but it can be used to split current, not necessarily limit current, but you're splitting current, which is a whole different thing. But I'm not going to go into that. Maybe next class, or maybe another class I'll go into that. So the reason why we put that resistor in there, though, is because we are limiting both the voltage and the current that is able to go through it. For example, if I was to actually hook up, by increasing the resistance, we are technically decreasing the current, but it's not. It's actually splitting the current. If you take that ground wire and hook it directly, don't do this, by the way. If you hook it directly up to, say, A5, your LED will work, but it'll be really, really bright, and it will not work for a long time. If you put a different resistor in the circuit, good question. Go ahead and try it, Tyson. You got the 10K? Go ahead and put the 10K in there. See what happens. You got to think about what happens when you do put the 10K in there. You're decreasing the amount of amperage, so your light might blink on and off, but it'd be a whole lot dimmer. He should not blow up. No, he should not. Tyson, don't blow up. Jacob's worried about you. You can all do it if you want to. Just to see the difference in what happens. All right. How much time I got? One thing I did not mention while y'all are doing this, the comments. So here in this example code, you'll see these grayed out words. All right, these are just comments. They are not read as part of the code. There's two different ways of doing them: // and then /*, and then */, which gives you a paragraph. All right, here's a single line comment and multiple line comments. Now, there will be times where most of the time we're writing stuff, I'm not going to type out the comments because they take a long time, but some of them I will be very specific about because I do want you to know what a particular line of code is doing. So I will specify the important ones versus the non-important ones as we go on. These curly brackets or braces, right? This is what keeps your code in order. So here's a curly brace, and here's a curly brace. Notice how for every open one, there is a closed one as well. All right? For every open one, there is also a closed one. And the same thing goes with parentheses. For every open parentheses, there's a corresponding closing parentheses. All right? And sometimes the curly brackets can get kind of confusing because this one correlates here, and this one's here. But I could have, 8,000 lines of code. So that one could be way, way down there at the very, very bottom. All right? And you wouldn't know it. I need to find out how to put number lines real quick. Let me figure that out. Can I put? Nope, I can't put lines on. Dadgummit. That's why I don't like Arduino. So how many times does void setup run? Is it an indefinite loop? I got one correct answer. Good job, Dennis. Tyson, you're wrong. Hate to tell you. I don't know what they're trying to do here. Oh, okay. Correct. Got a few more. So void setup in Arduino runs only one time. Now we're not going to have time to do this one here. So the semicolons at the end of every statement that you saw, those are like periods. All right, semicolons are like periods. As far as it ends, kind of like a closing statement or a closing thought. However, you could have multiple lines of code, but only one semicolon. But the majority of the time, you have one semicolon per line of code. I will denote each one of those. funny story, true story. Was it last year or a few years ago? I was up till like 3 o'clock in the morning coding, and it was like a lengthy code. I was probably at, I don't know, 1,000 lines or something. I don't remember how many. It was long. And then like right after that, I had to switch gears and start writing a paper. I got like halfway through that paper till I realized every single one of my periods ended up being a semicolon. Like every time I was meant to put a period, I just kept typing semicolon. So yeah, I had to go back and change a few things. The problem was I wasn't even looking at my screen to notice. Yep. Sucks being a fast typer because yeah, I just sit there and yeah. All right, comments, etc., etc. Yeah, we're not gonna have time to hook up this circuit. Oh, notice here. So like when I told you to hook up the green wire to ground, right? There's several different ways of doing that. And actually, we're going to go ahead and cover one right now, so this will save us a little bit of time. So I want you to, for this specific time, and there will be times where you cannot do this, but for right now you can. You can leave your Arduino hooked up. You can unplug your ground wire that you had in, what the have you in? A13. I would just want you to plug it into the negative rail, right? Here is blue, but on yours is black. The negative rail of your Arduino. And then you can just jump that resistor all the way over to anywhere on that negative rail, and your circuit should work exactly the same. All right? And go ahead and try to do that. Make sure it's going to work. And yes, you can leave it plugged in for this time. There will be a few circuits where I'll be dead set on y'all not doing that, but for right now, I'm not. Cool. Cool. So it's the exact same circuit. We just hooked it up slightly differently. You could technically do the same thing for the power, but I don't want y'all to do that because we're not using the 5-volt power. So let me show you. So here in all these diagrams we're using, he has this 5-volt plugged in here to the power rail. We're not going to be using that all the time. We're going to be mainly dealing with the power from this side, from here for some reason. All right. So from here on out, I do want you to connect your grounds like it's set up here. Like this ground is going from here to the breadboard, from here to here. So for any circuit that we hook up, go ahead and assume that is going to happen. That way, when I do label out how to plug things up, I'll just say plug your resistor into ground, which is going to be this row. Does that make sense to everybody? Does everybody capiche? Comprende? Understand? What's up, Mr. Wade? Saw your hand go up or then down. Then now I'm confused. Josh, get that? Jacob, Dennis, Celsi. Everybody get what I was trying to say there? Tyson. All right. So in the circuit that do you have the original circuit hooked up, Celsi? All right. So if you take that green wire out, that green wire that you have here, hang on, let me go to the next slide. I think that'll make it more sense. So right now you have this green wire here, and then it's coming over here towards, towards the resistor somewhere. I don't know why I did that. I got PID control on this. I gotta get rid of that. Control here, all right, to the resistor. What you can do is this is the green wire from this ground. I'm just jumping it over to here, to the bottom part here, and then you can just take the resistor where you had it plugged into the green wire and then jump it over to here. Does that make sense? Okay. So now, from now on, I will not say plug it into, or I might say plug it into ground. But when I say ground, I'm going to be referencing this here. All right, not the Arduino itself. You should already have this wire hooked up. All right. Take care, Mr. Wade. All right, and then, all right, so 2 minutes left. How would y'all like to see the robot that I spent this weekend building for y'all? That y'all will hopefully get to build this semester. Yeah, you just want to show it off to your sister. All right, let me find it. Ooh, I forgot all about that, Josh. I'm so sorry, dude. I usually don't forget that. All right, hang on. Let me write that down again. Josh, program, and all right, I'll check into that, Josh. So there it is. Granted, you probably won't have this tape on there for the sensor. That's just a distance sensor. There's going to be a whole lot more wires attached to it. But it has big old wheels and stuff like that. There's the Arduino. I need a name for this robot, though. Be looking something like that. This is going to be the bottom side. Ignore my very, very messy desk. This is going to be the caster, the steering, and battery pack. I need a name for the robot. Y'all got any good names for a robot? What y'all think? I'm not calling it Josh. Not going to happen. Is it Clutch Master 2000? Tyson suggested Josh. It's not quite Jarvis level. It's not quite Wally level. So we need to step it down a little bit here. So Larry. Robot Larry. You know what? I'm kind of like it. Larry. I'm kind of liking Larry. I'm not, that's my other class. But right now, Larry's sticking. All right, y'all. Any final questions? Any engineering? Anything class related, future related, past related? I do everything except personal advice. Now, as we go on, hopefully this process will hopefully get a whole lot faster because y'all get a whole lot better at hooking up circuits. What's up, Jacob?
Unmuted. What's up, Jacob? Oh, nothing. I'm raising my hand.
All right. Yep, Robot Larry. I'm liking Robot Larry. Nobody else? All right. Going once. Going twice. All right. I'm going to bid y'all adieu.